Here are some examples of using the derivative rules and properties that we've seen so far. Here we're going to differentiate by combining the power rule and the derivative properties. Okay, so our first function that we're going to look at is f of x equals x to the 15th power plus 2x to the 9th power minus 5x to the negative 4th power. Okay, this has got a little bit of everything in it. So we're going to find the derivative. That's differentiation here. We can write that as f prime of x. And according to our sum and difference property, taking the derivative of this polynomial here, this polynomial, is going to utilize that sum and difference rule because we have a sum between those two terms, we have a difference between these last two. So we can write this in the Leibniz notation that I've been using so far, x to the 15th plus 2x to the 9th minus 5x to the negative 4th. And then that'll really let us see that, okay, we can use the sum and difference properties to split this up into the derivatives of x to the 15th and then plus the derivative of 2x to the 9th and then minus the derivative of 5x to the negative 4th. Okay. And once we've done that, the first term here, the derivative of x to the 15th, that is just a direct power rule. So we're going to bring down our little exponent there, bring it out in front as a coefficient. So bring the 15 out front. So 15, and then lower the power on x by 1. So 15 minus 1 is our new exponent there. Okay, so that'll do that derivative. For the next one, next term here, derivative of 2x to the 9th. We have a constant multiplying x to the 9th power. So let me note that, constant multiple. We've got another one over here, by the way. And so we can say that this is going to be the same as taking that constant times the derivative of x to the 9th. So 2 d dx of x to the 9th. Okay. And then might as well do that on our last term here as well. That's going to be minus, bring our constant multiple out. So 5 times the derivative of x to the negative 4th. Okay, so here we have 15x to the 14th power, and then we'll have 2, and the derivative of x to the 9th, now we can just use the power rule on that. Okay, so we're going to take our 9, bring it out front as a coefficient. Okay, 9x to the 9 minus 1 power. And then we'll do the same type of thing over here with our last derivative. We've got our negative and then our 5, and then we'll have that negative 4 brought down out front as a coefficient. I'm going to stick a parentheses here, negative 4 x to the negative 4 minus 1 power. And the last step is just to clean this up. So we have 15x to the 14th plus 18x to the 8th power. And then negative 5 times negative 4 would give us plus 20 x to the negative 5th power. And that is the derivative of this function right here. There's f of x highlighted, And now this is f prime of x, the derivative. So wasn't that so much faster and nicer than the limit definition? These rules are pretty awesome. All right, let's do another one here just to see what this can do for us. Okay, let's call this function g of x, just to switch things up. And this one will be 5 times the cube root of x squared plus x squared times the 5th root of x cubed. Okay, now you might look at that function and say, what are you doing? That does not look like what we've had so far. Here we have an x squared and a radical, and we got all sorts of crazy roots going on here, cube root, 5th root. And so, yeah, you're right, it does look weird right now. We can't use our rules directly on this function in this format, but we're going to do a little bit of rewriting, and it's going to be so much nicer, and we'll see how we really can apply our power rule and our properties. So for rewriting this is still just g of x. We're not taking the derivative yet. We're going to switch these radical terms over into rational exponents. So if you need to refresh how to do that, Google rational exponents or look it up in the study plan or email me or talk to me. We can go over it. But this cube root of x squared, for instance, here, that's going to become an x to the 2/3 power. This exponent goes up in the numerator right there, and then the type of root goes in the denominator. Okay, so 5x to the 2/3 plus x squared, and then this 5th root of x cubed would be x to the 3/5, 3/5. Okay, and now a little more rewriting because we're not quite there yet. All right, the 5x to the 2/3 is okay. We've got a constant multiple right here, and then this can be handled with the power rule. So that term's all right. But we don't have anything for multiplying two terms with x's. This is not a constant multiple because it's got the variable in it. So what we're going to do here is we are going to combine the exponents. Okay, exponent rules here. Add these two together. Okay, 2 plus 3/5. That would be 13/5. So that's really x to the 13/5 power. Okay, which that now can be handled with the power rule for a derivative. And so that's what we're going to do. Now we're taking the derivative. So in your notation, make sure to be very clear if you're just rewriting the function g of x, like if you're just doing exponent rules or rational exponents or something, don't write a prime in there yet. No ddx in that bit. But then once you start taking derivatives, make sure you do put a prime in there or write your ddx, because now this is not the same as the original function. Okay, the derivative is an entirely new function, so we've got to notate it as such. Okay, so we're going to take the derivative of 5x to the 2/3 power plus x to the 13/5 power. First things first, get our sum rule going there. Separate these out. Derivative of 5x to the 2/3 plus derivative of x to the 13/5. Okay. And then we have a constant multiple right here, the 5 times that power of x. So Bring the 5 out. D dx of x to the 2/3. And then here, in the second term, there is no constant multiple. We can just go straight for the power rule. So take that power of 13/5, bring it out front as a coefficient. 13/5, and then x to the 13/5 minus 1. Okay, got to work some fractions here. All right. So let's see, we have 5 and then our derivative of x to the 2/3. Now you can bring that 2/3 out as a coefficient. 2/3 x to the, I'm going to make a little side note here. 2/3 minus 1, 2/3 minus 3/3, that would be -1/3 power. -1/3, there we go. And then plus 13/5 x to the, okay, 13/5 minus 1, that would be 13/5 minus 5/5, so that would give us 8/5, 8/5. Okay. And then just to finish this off, make it look nice and pretty, I'll multiply these two terms together here. 5 times 2/3 would be 10/3 x to the -1/3 plus 13/5 x to the 8/5. Whew. All right, it's a crazy looking function, but there it is. You could put this back in terms of the roots or radicals if you wanted, but it's just fine to leave it just like this for now.